We seem to be live. There's some disconnect. I'm obviously streaming live from a different site than the medical college, but I seem to need something to be switched on there so that the streaming can work from here. I'm a little techno challenged. I don't exactly understand how it goes, but it shouldn't be so tough that I have to depend on somebody. Anyway, I'll address that problem later. Let us continue where we stopped. Alright, so we were here and we said there were several types of nerve endings, sensory endings, slowly adapting and rapidly adapting, mechanoceptors, thermoceptors, nociceptors. But the large number of them seem to be mechanoceptors. That means they sense a disturbance in their environment and they relay that sensation via the nerve to the nerve cell body, which will take it further towards conscious or unconscious parts of your CNS. Then let us look at, apart from this whole bunch of things which we call motor neurons and another whole bunch which we call sensory neurons, which are of different varieties, we have a certain set of certain specialized structures, derivatives of the nervous tissue itself, which are going to be subserving what we call proprioception. That is the sense of activity at joints which are mobile, right? So it is a sense of position and movement at a joint, particularly your musculoskeletal system, synovial joints, but also the partly mobile joints. Remember, there were mobile, immobile, and partially mobile joints. So the immobile joints, obviously there's nothing happening there, there's nothing to sense. But in the mobile joints, a lot of movement is happening, different grades and power of movement are happening, and all that sensation has to be sent back, particularly to one part of your brain called the cerebellum. It's a large part which has been evolved lately quite heavily as we have climbed the evolution tree, and a good amount of volume of tissue has been given for this control and coordination function of your nervous system, right? So the structure and innervation of a Golgi tendon organ. Golgi, again, the name of the scientist who discovered this and who described it. So we know that the nerve cell cytoplasm is called the neuroplasm, the cell membrane will be called the neurolemma, and it will be surrounded by a little bit of fibrous tissue which is giving it support and holding it together. So the neurolemma is the endoneurium, that is the innermost wrapping of the neural cytoplasm, outside of which there will be a perineurium, and outside of that will be an epineurium. We'll look at the histology later, but because in this case they have named those words, I am again trying to define them. The perineurium and endoneurium here have not been drawn. They've been omitted as if they don't exist, so that you see the nerve fibers coming here and ramifying between the collagen fiber bundles of a tendon. So in other words, we are not looking at the muscle, we are not looking at the contractile or structure or tissue which we said is muscle. We know that muscles are inserted, the ends of those muscle fibers are inserted into non-contractile mechanical structures, rope-like structures called tendons, which are essentially bundles and bundles of collagen fibers, very symmetrically aligned to be able to transmit mechanical force in a particular direction, dominantly in a particular direction. That molecule is so aligned, it is lengthened out, it has got little branch structures which interlock with side ones, and it is extruded out in close juxtaposition, so that all those molecules together form a very tight and very strong structure which can relay kilogram force, right? So muscular contraction will be relayed to the tendon or a modification called an aponeurosis. We will come to that later. But this rope-like tendon is what will actually attach to a bone and pull on it or push on it. So the collagen fiber bundles in the tendon have got the nerve endings on them. So far we were looking at nerves ending on nerves forming synapses, or ending on muscles forming neuromuscular junctions, which could be of a motor end plate type, or they could be of a relay type which ends in the smooth muscles of your viscera. And we didn't so far yet see that the nerve endings were ending on any other kind of tissue. But here we are seeing they are ending on the collagen fiber bundles of a tendon, which is a different tissue but still belonging to the musculoskeletal system. And these are motor fibers which are ending on this, and they are ramifying with the same button-like or knob-like endings. The muscular contractile part has ended here. The muscle fiber, contractile fiber, myocytes have ended here. The collagen has started and is being laid down in bundles. On that collagen bundle structure also we have some nerve endings. This combination of nerve ending with the tendon material is called a Golgi tendon organ, and we are showing it as if there are nothing else, as if it's a bare nerve ending, but actually it will have an endoneurium, perineurum. It will have a wrapping of its own fibers. It has been omitted in this particular diagram. We will look at how that functions more in physiology. They'll tell you all about it, just as they will classify neurons and divide them according to their diameter, according to the speed of action, according to the actual function that they do. You please remember and go through that classification as and when it is done for you. Apart from this whole bunch of motor neurons, a whole bunch of sensory neurons, different kinds of motor neurons which are available in different parts of your musculoskeletal system and in parts of your visceral system, but still essentially either sensory or motor. There is one third bunch of neurons, nerves, which are doing neither motor things nor sensory things. They are not giving instructions directly for anything to happen, either for a muscle cell to contract or for a secreting cell to secrete. But rather, they are going to be like information relay messengers, right? Couriers. And don't use that in your exam, but it's just to give you a concept of what integrative neurons do. Some of them are highly sophisticated in the sense that the way they interact with the surrounding other neurons is they are able to modify the information which goes through, which makes it a very advanced function, right? If you're simply taking an information and giving it away, it's a simple function. But you're receiving certain amounts of information, it's all flowing around you in several kinds of junctions. And you take 3,000 bits of information, but let go only 250 or 2,742 in particular directions, then you are a bigger brain, right? So again, please don't write all this in your exam paper. This is just to illustrate to you that integrative neurons, though we always thought in the beginning, when I was studying, we had this kind of a mild concept that they are of a sharing kind of nature. They share information around. That in that whole neuropill, that's a word again you will come across in histology, and I will explain it in detail later. But essentially, in a territory where several kinds of neurons are intermixing and matching with each other, some bits of them, some endings of them can do certain things, and some other endings can do other things. The actual biochemical molecules which are being released are different, and the quality of the molecule is such that certain neurotransmitters or GABA or serotonin can do certain kinds of depolarization, whereas others can't. So that mix, that complex mix, allows a certain amount of integration to happen. So most of the neurons participating in this function, we call them integrative neurons, and they have certain types and certain shapes. So many of them are of a pyramidal shape, where they, like a base of a pyramid and then three sides, so four-sided cell body, which to the three of its sides will have a dendritic tree, and the fourth side, actually it's not a tip but rather the base from which the axon will go. So this is a tape shape, typical shape of a pyramidal cell soma, which will have basal dendrites, apical dendrites, and an axon. This assumes that it has a predominant direction. One of its corners is going to, if you're calling its apex. In a pyramid, you can lie a pyramid on its side and then the apex will change, isn't it? If you actually have a proper tetrahedron, four-sided pyramid. But here in this case, we are saying that one of its tips, angles, corners, is going to be called the apical end, and it will have one bunch of dendrites and it will have other dendrites. This differentiation has been made because the apical dendrite information is coming from certain sources and basal dendrite information is probably coming from some other sources. So territories of receiving information are not the same for all the dendrites, right? They are not uniform. They're not democratic. They're again very specific whom they talk to, or whom they receive information from. Axon, of course, takes away information from the cell body to the next generation of neurons. So this is one kind of integrated neuron which is of a pyramidal cell shape. Then you have a very specialized one called the Purkinje cell. Dr. Purkinje was a phenomenal man and he did many things in neuroanatomy, neurophysiology, and a whole bunch of contribution has come to neuroscience by him. So this particular neuron described by him is a large cell ovoid body, first noticed and identified and named by him and described. Its function also was described to some extent, after which a lot of follow-up research has elaborated on what we knew from his generation. So this Purkinje cell soma is a ovoid cell which has a different look. It has a dendritic tree which looks like a crown, right? It looks like it's a bipolar neuron, one pole here, one pole here. From here, immediately a whole slew, a very rich network of dendritic tree has come. But again, if you look at the territory in which that dendritic tree is spreading, it seems to be a very circumscribed shape, a slab of area from which it is taking information. And then the next Purkinje cell will have its own slab of area, and then the next one. So they're laid down in a neat, like a row of soldiers, each having their own territory of incoming information. And their axons will lead out the outgoing information in one different, in the opposite direction. And the axons of parallel Purkinje cells will all be parallel, sliding up like that against each other in the way they end. So this is happening particularly in the cerebellum, and it is an integrative type of neuron. Then you have interneurons, which are literally only that. They are just couriers. They are going to be between all the other more important, more integrative neurons over there, and they're only going to relay information. So they will receive from dendritic ends and they will give away to axonal ends, and or the other way around. This doesn't matter the direction in which you are. The difference between this and this is your dendritic tree is much limited. Most interneurons have limited number of cell processes compared to the sensory neurons or specialized integrative neurons like the Purkinje cell. And this I just inserted it because it's such a beautiful picture. I never get to see this actually, because you need a very specialized nerve stain and you need a very high magnification to be able to stain only integrative neurons, not motor, sensory or any other kind of neuron, and to be able to see its territory, its tree of processes, cellular processes, neuronal processes. But it's pretty, and you can see it's kind of beaded in appearance, right? So it's different cell processes are having, they seem to have taken up a stain in a beaded fashion, and some processes are looking a lot more dominant than the others. But the point to remember is that to be able to get this information from this kind of tissue, very difficult to work with neurons in a live state, in a live animal, right? In a live tissue, because nerves die very quickly and very irrevocably, almost impossible to repair them or regenerate them. So to do any neurophysiology experiments is a huge challenge, but still some people have attempted, they have designed, they have executed, they have got the information, they have corroborated it, and they have established that this is how our body works. So remember, apart from motor and sensory neurons, we have integrative neurons, two of which are named pyramidal cell types and Purkinje cell types, but the whole other bunch, the rest of them, if they don't have any specific name, they are all called interneurons. All right, the peripheral process, right? The peripheral nervous system. Already jumping into that. I'm only looking at one component of it because again that will be dealt with in great detail in physiology, where you have a process and a phenomenon called myelination. We already mentioned it. I think you have heard of it before, and again it will be dealt in detail by the physiology people. So we will look at it in specific areas later. As a systemic overview for the nervous system, we must know that many nerve fibers, particularly the large diameter ones, the alpha neurons, will be myelinated in nature, meaning that the nerve cell cytoplasmic membrane, the neurolemma, right, the neural membrane, is containing the neuroplasm, which is a cytoplasm in which there are all kinds of cell organelles and bodies and vesicles and so on and so forth, and there is a flow of material inside that neuroplasm in one direction. In dendrites, it is towards the cell body or soma. In axons, it is away from the cell body or soma towards the tip of the axon. That is the general plan of action. Outside of that neural membrane is a thick layer of lipid which is laid down. It is not a cell. It is just material, fatty material, made up of lecithin and sphingomyelin, which you will learn in biochemistry in detail, which is extruded and laid down by its secreting cell. So there are some cells which are laying down this myelin sheath within the central nervous system, and there are other cells which are doing it in the peripheral nervous system. We will do that when we do histology. What you need to know is, therefore, nerve fibers, that means the cytoplasmic process of the neuron, will be myelinated to a large extent. I told you it serves as a electrical insulation, so that information passing within one cylindrical fiber is not confused or not shared or not impinging upon information in the next one, even within the same bundle, keeping the incoming information very sharp and the outgoing orders very clear, very pointed, right? So if I want only 10 fibers of my joint to contract, to bring out a small amount of information, there are 1,000 fibers in the bundle in which it's traveling. The 990 should not get the order. Only the 10 should get the order, right? So there should be sharp insulation between these fibers which are carrying the motor orders particularly. Similarly, sensory. If some amount of stimulation of my peripheral 6 types of nerve endings is coming in, then the fact that fiber number 1, 2 and 3 are stimulated, 4, 5 and 6 are not stimulated, that must be kept sharp so that my sensory cortex can precisely identify, the mosquito is sitting on the tip of the middle finger, and not confuse it with anything else, right? This is the whole point. So coming back to myelination, it is for the purpose of insulation, but also there is a phenomenon where myelination is interrupted and you get a little bit of bare neural membrane. Then again myelination is continued. Then again it stops. That means one cylindrical piece of neuronal fiber, cytoplasmic process, is wrapped in fat. Then suddenly there is a gap. Then again the next piece is wrapped. So in that gap, that nerve fiber is bare. And electrical conduction happens in such a way that when there is a depolarization of plus minus ion differentiation, the electrical impulse tends to jump from a bare point to another bare point, not having to flow through the center through a cytoplasmic flow. Now, a physical flow of anything, a vesicle or a organelle, will take an X amount of time. Electronic conduction of impulses is thousands of times faster. So the provision of a myelin sheath and its architecture as an interrupted sheath over succeeding segments of the nerve cell process is a marvelous phenomenon which allows very, very rapid conduction of the electrical impulses called saltatory conduction, which again they will teach you in physiology. I'm just telling you the anatomical basis of it in a longitudinal section. LS means longitudinal section. When you see, why I put it in inverted commas is muscle is also a fiber, collagen is also a fiber, nerve is also a fiber. It's very, very confusing. That's why I'm using the word cell body, cell process, cell membrane as much as possible, so that you will establish it in your brain. What I mean by fiber is essentially just one cell's process for a nerve. In muscle, I mean one cell, one multinucleated syncytial skeletal muscle cell is equal to a skeletal muscle fiber. And when I'm saying it in connective tissue, then I'm meaning one collagen molecule is a collagen fiber. It's one single heavy molecule. A whole lot of atoms in it, thousands and thousands of atoms in it, in a particular geometrical arrangement, which gives it a linearity and a tensile strength. Alright, so we still use the word fiber because to the naked eye, all of them look like stringy little things. When you see it in dissection, each of them will look like a string, all of them will be creamy white or grey in color. Very difficult to differentiate from each other. But you must have the systemic overview somewhere in your head, so that when you actually see what is it, you can say, Acha, this could be this, this or this. How will I know? I will trace it. I will trace it forward, I'll trace it back. We'll see where it is coming from, where it is going, what branches it has. Then I know, Acha, this is what it must be. Plus, of course, we will teach you what to expect, so that then your eyes will see it. Otherwise, you'll just see a gitch-bitch network. Right? Okay. The last thing, today's class, apart from neurons, your nervous system has 10 times or 100 times the number of cells of neurons is supporting cells which don't do conduction of impulse of any sort. No sensory impulse, no motor impulse, no interneural impulse, no integration, nothing. They are supporting cells which are purposed with nourishment. They bring nutrition to this whole bunch of extremely sophisticated, extremely specialized, very vulnerable cells. And to some extent, they are able to modify the environment in which all this zapping electrical impulses are going on all the time. So neuroglia are important. We neglect them, we don't worry too much about them. The second important applied aspect I want to mention is that neurons, because they cannot divide, they cannot form tumors. They've given up the capacity to divide and form copies of themselves. No mitosis, no meiosis, nothing is possible. Because once they become their full form, that's all they will do till the end of life. They have to be kept alive. Right? Neuroglia can divide, so they can form tumors. So if you're going to have a patient with a brain tumor, it's not going to be from neurons of any sort. It's going to be some form of neuroglial cell or some form of wrapping cell. You've heard of pia matter, arachnoid matter, dura matter, right? So the wrappings of the CNS, they have cells which can still divide, and that can cause tumor formation. Just keep this as a background concept which you must not forget and which we will show you later. So inside of a CNS slab, this is extremely high magnification, very, very pictorial, very schematic picture, just to show you all the kinds of neuroglia that we have. They are non-neuronal cells in the CNS. They have a particular structural organization and interrelationship with each other. So on the one side, you have the covering of the brain, which is called the pia matter, which seems to be made up of fibrocytes of some nature, right? On the other side, you have the central cavity of the CNS, which contains a liquid, right? These are called the ventricles of the brain, which contain the cerebrospinal fluid. Right? So in the thickness of your brain, or the outer wrap is pia matter, and the inner lining of the cavity containing the liquid is the ependyma, the kind of cell which forms the lining of that ventricular cavity. It's called the ependyma. This also lines the central canal of the spinal cord, which also contains the same cerebrospinal fluid or CSF. So the shape of the ependymal cell is somewhat like a cuboidal cell. It seems to have some cellular processes towards the liquid, the CSF, and some longer processes also. And then it has some basal processes which is impinging on all the nerve matter, neural material stuff which is there in the thickness of the brain slab. So the kinds of cells which are available here, the neuron itself is the big cell. It has a big soma, it has dendrites, it has axons, it has all of that going on. So these seem to be dendrites, and this long one which has a myelin sheath, it seems to be an axon. This is supported by cells called astrocytes. Astro means star. So the minute you look at any neuroglia, it is more or less star shaped. It's got a whole bunch of almost equal sized processes. No dominating short or long, no dominating axon, very long process, right? And not that rich network of dendrites which we normally expect from a neuron. It has a whole bunch of spray of processes in all directions of almost the same dimensions, almost the same diameter. It's called an astrocyte, and these processes will go and end either on the pia mater through a structure called an end foot, or it will end on the axon of a nearby neuron, or on the soma, or on the dendrite, whatever it is, on a neuron. So that is called an end foot. So astrocytes will have end foots of their processes. We don't call their processes dendrite, axon, anything. We don't give any special name to their cell processes. So astrocytes will have a few thousand processes. Many of them will have a flat ending, like a flat plate-like ending, which will be on the pia. Then we'll call it a subpial end foot. If it's on a neuron, we'll call it a perineuronal end foot. It doesn't matter. The point is that astrocyte is going to many different kinds of cells in its vicinity, especially to the neurons near it. Not only one neuron, but maybe many neurons. So one astrocyte will be interrelating with many neurons, not only one. This one is also an astrocyte. This also has many kinds of end foots. It's on the inside layer, so it is interacting with the ependymal layer and with processes of an ependymal cell, and with the neuronal body, and with the neuronal dendrite, and with a blood vessel. So this is a capillary. It's got blood flowing within it, and this astrocyte's end foot is landing on the capillary. So the third type of end foot which you're looking at is a pericapillary end foot. So any kind of astrocyte will connect with different tissues within the CNS, largely many of them neurons, so they are the dominant cell type, but also pia mater layer, also ependyma, also blood vessels at capillaries. Then you have a second type of glial cell called an oligodendrocyte. The name oligo means less, dendro means dendrites, processes. Compared to astrocytes, the green ones, these oligodendrocytes have very few numbers of processes. They don't have thousands, they have few processes. That's why they've given the word oligodendrocyte, and they are having certain cell processes which seem to be communicating with nearby structures and looking a little odd shaped. Homework, what could this be? Alright, and they seem to be relating with the axonal process of neurons rather than the dendritic side or the soma side. They seem to be relating more with the axonal side of the dendrites. So your homework is astrocytes and oligodendrocytes are obviously very different looking. They seem to have different location. What could be the difference in their function? And the third kind of glia, here it is light green, is a microglial cell which seems to be more on the ependyma side. It doesn't, in this picture at least, they don't show it relating to any neuron. They are much smaller in size, but where the name is micro, right? Microglia. Hint is, I already said neurons have to be kept alive. So between astrocytes and oligodendrocytes, somebody must be doing nourishment. Somebody must be bringing in nourishment, nutrition, rich material for this neuron to bathe in, for it to absorb from its environment. Please remember, your nerve cells are among the highest metabolism cells. They consume a lot of glucose and oxygen. So who's going to bring it to them? In my picture, the neuron is not talking to the capillary directly, apparently. Maybe the capillary materials are oozing into the pericapillary space and then being picked up by the neuron. Or maybe the astrocytes and oligodendrocytes are doing something about making provision for this sugar and oxygen to get into the neuronal cell. So homework is, please read up a little bit about how the biochemistry of the area is allowing neuroglia to be supporting cells to neurons as such. This is what I'm supposed to have finished today. The last bit is autonomic nervous system. We'll do it in 2 seconds because I'm not going into details. We will do this when we start dissection. There is the first 19-20 pages of your dissection manual is only an elaboration of the tissues which you will come across, and there, before we start dissection of the upper and lower limbs, we will go into the specifics of how the sympathetic system and the parasympathetic system are put together. So I don't want to repeat. Just remember, we have something called an autonomic nervous system, which means it is out of your voluntary control. It is on automatic, right? It is autonomic, self-governing. Its highest center is your hypothalamus, which part of your CNS. It consists of two equal opposite systems, which are called the sympathetic and the parasympathetic. The sympathetic system activation prepares the animal for a active response to a threat or a opportunity in the environment. You see food, you run after it, or you see danger, you run away from it. Either ways, the sympathetic has to be energized. And the parasympathetic system is called the rest and digest response, where the animal is in a safe, well-nourished state and goes into a kind of a reverse mode where internal organs start doing the work. The digestive system, respiratory, cardiac, whatever systems do rest, healing, repair, rejuvenation. Okay, so parasympathetic mostly brings about that. It's not always exclusively the case. It's not like if this is on, that is off. But very often it has to be. Only if one is off, the other can be on. Right? If you are actively fighting, you can't be also resting and digesting. So usually one will be completely suppressed for the other one to activate. But sometimes in certain areas, movements of the eyeballs, certain autonomic responses, there are combinations of activities which have to happen. We will see the loops of control which bring that about, and the anatomical architecture by which this whole function is served, so that it can operate without your conscious contribution to it. This is a part of the gut. This is the gut wall, supposed to be the stomach wall, right? Stomach wall. This is the lumen, this is the inside where the food is. This is the outside. So the kinds of signals which are continuously being exchanged so that this autonomic nervous system response can happen are of a two-toned nature. We call it neuroendocrine. I'm just introducing the concept here, but we will elaborate on it later. One thing which has to happen is sensation from our gut, right? Sensation is being picked up. This is a bipolar neuron, right? And it is going to go and give away the information somehow, somewhere. How? It will probably go into an afferent nerve fiber, which will go somewhere into the spinal cord. And from here, another bunch of nerves will take it to your autonomic part of the sensory system. A whole bunch of information is therefore neural in nature. Signals from the lumen, whatever is inside the gut cavity, what nutrients are there, what antigens are there, what irritants may be there, what secretions are there, are also being picked up as neurocrine signal. That means they're molecules, not electrical impulses, but molecules which are floating around here in the intercellular spaces of your gut wall, and also leaching through and getting into the environments around the gut. This is not neuroelectrical, but called neurocrine because it is somewhat like a endocrine nature, and some amount of information is going to a prevertebral sympathetic ganglion and then returning back into this particular environment. This is a little bit more deep and complicated, but remember there is one in between kind of stuff also happening. The ones which are easy to understand and straightforward is electrical signals which take sensation from gut wall, visceral sensation, and via spinal cord relate to wherever it has to go. Then the spinal cord, brainstem, hypothalamus, whatever centers are also receiving via the vagus system, the parasympathetic system, sensations which are going particularly to this particular 10th cranial nerve vagus, and this is not going via spinal cord but going straight to the brain stem. So there's a parallel amount of information which is also going there. Plus, in the tissue itself, tissue defense signals, local and systemic, are being provided. This is, you can say, somewhat lymphoid system directed. So there is an electrical neural bit which is very dominant. There is a neurocrine bit, somewhat endocrine in nature, because the lining cells of these are, some of them are endocrine in nature. They're able to take in some information and circulate it as signals, but they tend to be local in nature. They don't go all the way back anywhere central. They tend to be local and allow some amount of modification right there, only in that part of the gut, only for that bit of tissue, and so on and so forth. And another bunch of information coming from the defense systems, where these local immune signals are going to be shared, that information is going to be shared. So first we thought the nervous thing and the endocrine thing and the immune thing are all doing their own thing. But now we've realized that so much information is being shared, partly via electricity, partly via chemistry, partly via antigen antibodies, which is also one kind of chemistry. It's quite fascinating. So this control and coordination, inter-system integration, is a very much high level function. We don't think our humble gut is capable of it, but much of our autonomous control function, smoothness of action, adaptation to the rapid change in the environment is possible only because of it. Just keep that in mind. Wherever it is specifically relevant, we will be repeating it. Okay, I'll stop here for now. These are the remaining systems which need to be done. We'll take them up slowly, one by one. Goodbye for today.